Hi, I'm Mudinda and I'm here to help you understand maths better for free. Now, grade 11s and matriculants, today we're going to be talking about trig, particularly reduction formula. In 5 simple parts, I'm going to show you all that you need to know in reduction formula to the point where you'll be able to do a past exam example with me. Let's get into it. To start us off, let's talk about what I like to call normal reduction. Now, this is not a formal name anywhere in your textbook, it's just how I like to call this part. Firstly, here's a Cartesian plane that I've drawn. Remember that this point here is the 0 point, or 360. Here we have the 90 point, here we have the 180 point, the 270 point as well. But for now, let's focus in on the 0 or 360 point and the 180 point. A lot of times a reduction formula will refer to theta. When we say theta, we're actually referring to an angle that's less than 90 degrees. Remember, a 90-degree angle looks something like this. So an angle that's less than 90 is smaller, it's something like that. Now, what does it mean when we add an angle on a Cartesian plane? What does it mean when we subtract an angle on a Cartesian plane? If you're standing at the 0 point here, for example, adding an angle means moving anti-clockwise, that way. That's what adding an angle looks like. But moving clockwise is subtracting an angle. Now, if you were standing here at the 180 point and you subtracted an angle, in other words, you moved clockwise, and that angle was theta, an angle that's smaller than 90 degrees, you would end up in this quadrant here. And so that's why we nickname this quadrant 180 minus theta. If you were standing at the 180 point and we added an angle that's smaller than 90 degrees, you'd end up in this quadrant, and that's why we nickname it 180 plus theta. We nickname this quadrant 360 minus theta because if you were standing here at the 360 point and you subtracted an angle that's smaller than 90 degrees, you'd end up in that quadrant. Now, that said, if you were asked to reduce or simplify something like the sine of 180 minus theta, remember 180 minus theta is this quadrant where sine is positive. So you're allowed to reduce this to just become positive sine of theta. But if you were asked for the sine of 360 minus theta, well, 360 minus theta is here where cos is positive. Sine and tan are negative there. And so we are allowed to reduce this to negative sine of theta. Okay, so the reason we call this a cast diagram is because here in this quadrant, only cos is positive. Sine and tan are negative. Here in this quadrant, only tan is positive, cos and sine are negative there. In this quadrant, only sine is positive, tan and cos are negative. But here, all the trig ratios are positive. So now, what if you were asked for the cos of 360 minus theta? Well, 360 minus theta is this quadrant, where cos is actually positive. And so we can reduce this to be positive cos of theta. But what about the cos of 180 plus theta? Well, 180 plus theta is here, where only tan is positive. This would then be reduced to negative cos theta, because cos is negative there. What about the tangent of 180 plus theta? Well, that's here, where tan is positive, so this is now positive tan theta. And lastly, what about the tangent of 360 minus theta? Well, that's here where only cos is positive, so this would reduce to negative tan theta. This is what I call normal reduction, and I want us to now look at some examples of where you'd apply it. So here you're given sine of 360 minus theta multiplied by cos of 360 minus theta, all divided by the sine of 180 minus theta. All we'll do is we'll reduce each of these. Okay, so we know that the sine of 360 minus theta should be negative sine theta because 360 minus theta is where cos is positive. We know that the cos of 360 minus theta will be positive cos theta, and that the sine of 180 minus theta will be positive sine theta. Now, this sine theta and this sine theta can cancel out since everything here is multiplying one another. What we're left with is negative cos theta as an answer. Now, what about on this side? We have here the tangent of 180 minus theta times sine 360 plus theta over cos 180 plus theta times tan 360 minus theta. We know that 180 minus theta is where sine is positive, so this becomes negative tan theta. Now, grade 11s and matriculants, what happens here? What is sine 360 plus theta? We never spoke about 360 plus theta. But imagine you were standing here at the 360 point and you added an angle that's smaller than 90 degrees. You'd wind up in this quadrant where all the trig ratios are positive, including sine. And so that becomes positive sine theta. In our denominator, what does the cos of 180 plus theta become? Negative cos theta. What about the tangent of 360 minus theta? That also becomes negative. So it's negative tan theta. Now, if you have a look here, this negative tan theta can cancel this negative tan theta. So essentially, we're left with the sine of theta over negative cos of theta. I'll just put the negative in front of the fraction. But we know from trig identities that sine over cos is just tan. So this is negative tan theta. Be sure to watch the video we have on trig identities. Now, let's get into the second part. In the second part of our reduction formula topic, we talk about what we call cofunction identities. Grade 11s and 12s, please note that these have to do with cos and sine when there's a 90 and a 270, all right? Only. Now, what you will have noticed in our normal reduction is that trig ratios never changed. When we say trig ratio, we are referring to sine, cos, and tan. A sine would forever just remain a sine. A cos would remain a cos even after reducing. A tan would remain a tan after reducing. Now with cofunction identities, this is not the case. A cos will become a sine will become a cos. But this is subject to some rules that I actually want you to commit to memory. Now, if you have the sine of 90 minus theta, now I don't want you to memorize every single one of these. What I want you to memorize is the pattern that we observe, and I'll show you in just a second. See, if you have the sine, we're starting off with the 90 degree ones. If you have the sine of 90 minus theta, that changes to become cos of theta. If you have the sine of 90 plus theta, that also changes to become cos of theta. And if you have the cos of 90 minus theta, that changes to become sine of theta. What I want you to notice here is that with the 90 degree cofunction, a sine generally just tends to become a cos becomes a sine, right? Sine becomes cos, cos becomes sine. That's the general trend when you see a 90 degree cofunction. However, there is an exception, particularly the cos of 90 plus theta. That becomes negative sine theta. And that's why if you read the statement I've given for you here in the notes, the general trend is to change only the trig ratio. In other words, a sine becomes a cos becomes a sine. Except for the exception, which I've also shown down here in red, where both the trig ratio and the sine change. So cos of 90 plus theta becomes negative sine theta. It's just an exception. So I want you to remember this pattern, that when you see a 90 degree reduction, the general trend is to change only the trig ratio. But except if you see cos of 90 plus theta, there you change both the trig ratio and the sine. When it comes to the 270 cofunction identity, sine of 270 minus theta actually becomes negative cos theta. Sine of 270 plus theta becomes negative cos theta. Cos of 270 minus theta becomes negative sine theta. So what's the general trend that you're observing here? A sine becomes negative cos, and a cos becomes negative sine. Except for the exception again, cos of 270 plus theta. This one becomes just sine theta. So the general trend is to change both the trig ratio and the sine. except for the exception cos of 270 plus theta, where only the trig ratio changes. So I want you to commit these two rules to memory, that when I see a 90 degree, a sine becomes a cos becomes a sine, except for cos of 90 plus theta. That becomes negative sine. When I see a 270, a sine becomes negative cos, a cos becomes negative sine, except particularly the cos of 270 plus, which becomes just a sine. Are you sure you've memorized that? If you have, I want to give you a speed test. I want you to test yourself. I'm going to ask you some questions, and without looking back here, I want you to shout to the screen what you think the answer is. If you need a minute to memorize them, pause, memorize them, and then go ahead with this. What if I asked you, what is the sine of 90 degrees plus theta? What should the answer be? Cos theta, that's correct. And what if you had the cos of 90 degrees minus theta? What should this become? Sine theta, that's correct. When we see the cos of 90, we just change a cos to a sine. Now, what if you had here the cos of 90 degrees plus theta? What does this become? Negative sine theta. This is the exception of the 90s. What if you had the cos of 270 degrees minus theta? What does this become? This becomes negative sine theta. The general trend with the 270 is to change a cos to a negative sine. Now, what if you had the sine of 270 degrees plus theta? Negative cos theta. Again, the trend of a 270, a sine becomes a negative cos. Now, what if you had the cos of 270 degrees plus theta? Sine theta, because this is the exception. How many did you get right? If you got some of them wrong, go back here, give it a bit of some memorization of the pattern that we're observing there, because you have to know this for reduction formula. Let's go to the third part. Now, in the third part of reduction formula, I want us to talk about negative angles. You see, if you're given the sine of negative theta, this you can rewrite as negative sine of theta. If you're given the tan of negative theta, you can rewrite that as negative tan theta. But weirdly, for some reason, and we will explore that reason, the cos of minus theta becomes positive cos of theta. Let's talk about why, and I'm going to explain this in two different ways. Firstly, imagine you were standing at the 0 point and you subtracted an angle, because that's what it means to have a minus theta. Subtracting an angle means moving clockwise. You'd end up in here, where cos is positive, sine and tan are negative. That's why the sine of negative an angle is negative sine theta. The tan of negative an angle is negative tan theta. But the cos of negative an angle is positive cos theta. Because this minus theta simply means move from the 0 down to get here. Another way you can think about it, or an alternative explanation, I want you to know that you can always add 360 degrees to any angle. For example, the sine of 30 degrees, if you put this in your calculator, you would get a half. Now, let's add 360 to 30. 360 plus 30 is 390. In your calculator, if you put sine of 390, you'd also get a half. So, as we can see, sine of 30 and sine of 390 is the same thing. Why? Because we are allowed in maths to add 360 at any point. If you're standing right here at this point and you add 360, you'd be back to the same point. And that's why we're allowed to add 360 at any point. So now imagine you had the sine of negative theta and you added 360 to it. It would now be the sine of 360 minus theta. But what is sine 360 minus theta? It's negative sine theta. On the other hand, if you had the cos of minus theta and you added 360 to that angle, you'd have cos of 360 minus theta, and we know that that's positive cos theta. That's just an alternative explanation to convince you why this is true. Let's look at the fourth part in our reduction formula topic. Grade 11s, matriculants, what would you reduce sine squared of 360 minus theta to become? Now, if you screamed to the screen that, well, I think that'll become negative sine squared theta. Unfortunately, you're wrong. Now, you might think that because 360 minus theta is where cos is positive and sine is negative, and that's correct, that's right. But I'd encourage you to expand this a little further. Instead of just simplifying it directly, remember that the sine squared of 360 minus theta is the same as the sine of 360 minus theta times the sine of 360 minus theta. That's what squaring means, isn't it? And like you said, the sine of 360 minus theta is negative sine theta. But now, when you're multiplying it with another negative sine theta, what's going to happen? The answer will actually be positive sine squared theta. So be very careful when you're squaring angles. Instead of just simplifying them directly, I suggest that you expand it. Great. Let's look at the fifth part in our reduction formula topic. In the fifth part, I want us to talk about special angles. Now, special angles help us determine sine, cos, and tan of 30 degrees, 45 degrees, and 60 degrees without a calculator. Guys, one day my handwriting will be much better. I believe it. Thank you for not complaining about it, but it will be better one day, I promise. Luckily, handwriting doesn't really matter with maths. Whether you're messy or you're neat, as long as we can read it and follow it, you'll get marks. So, you guys are no strangers to special angles. We learned special angles starting in grade 10. We know that it's these two magic triangles that we use. One of them has 30 degrees here, 60 degrees there, 1 here, 2 here, and root 3 there. The other one has 45 degrees here and there, then has 1, 1, and square root of 2. You need to memorize these two triangles. You need to know them off by heart. Why? They help us to know the sine, cos, and tan of 30, 45, and 60 degrees without a calculator. For example, just by looking at this triangle, I can find the sine of 30 degrees. We know that sine is opposite over hypotenuse, so I know that it's a half. What about the tangent of 30 degrees? That's opposite over adjacent, so 1 over root 3. And what about the cos of 45 degrees? Well, that's adjacent over hypotenuse, so 1 over root 2. And what about the sine of 60 degrees? That's opposite over hypotenuse, so root 3 over 2. These are your special angles. And why is it important that you know them? Well, we're going to be using special angles and what we've learned in reduction formula so far to reduce big angles that we're not very comfortable with. So we're going to be using reduction formulae and special angles. Now, I'm going to illustrate how to do this through examples. But what I want you to keep in mind is whatever big angle we get, we're going to compare it to either 90 degrees, 180 degrees, 270 degrees, or 360 degrees. In fact, I would suggest whatever it's closest to. Sine 120, for example. I think that 120 is closest to, I think 90 degrees. So I could say, what's the difference between 120 and 90? It's 30 degrees. So I can rewrite this 120 as 90 degrees plus 30 degrees. Why am I allowed to do that? Because I haven't changed anything. 90 plus 30 and 120 is the exact same thing. Great. But now, imagine instead of 30, you had theta. What would you do if you had the sine of 90 degrees plus theta? Well, we know from cofunctions that would be cos of theta. For that reason, I'm now going to reduce this to be cos of 30. The only difference between this and that is that theta has now become an actual number, 30 degrees. Now, from my special angles, I know that the cos of 30 would be adjacent over hypotenuse, so the answer to this is actually root 3 over 2. And that is how we use special angles and reduction formula to reduce big angles that we're not used to. What about the cos of 225 degrees, for example? I think that that's closest to 180. So what if I said cos 180 degrees? And what's the difference between 225 and 180? 45 degrees, right? And so I can rewrite this as 180 plus 45 degrees. But you see now, cos of 180 plus 45, 180 plus theta is where tan is positive, cos is negative. So this is now negative cos 45. Now, if you use your special angles, cos 45 is adjacent over hypotenuse, so it's 1 over root 2. And that's the answer. Now, I just want to make it very clear that it actually doesn't really matter which one of these you use. By that I mean whether you went with 180 or you went with 270, it doesn't really matter. Because if I took cos 225 and instead of comparing it to 180, I compared it to 270, well, what's the difference between 270 and 225? It's 45, isn't it? So I can actually rewrite this as the cos of 270 minus 45. It's 270 minus 45, that's 225. Now that said, what do you do when you see the cos of 270 minus an angle? Well, you reduce it to negative sine that angle. That's what we learned in cofunctions. And what is negative sine 45? Well, sine 45 would be opposite over hypotenuse. So it would be negative 1 over root 2. As you can see, it got us to the same answer. Even if you used something like 360 or 180, you would most likely just come back right to the same answer because maths is so beautifully designed. Now, what about the tangent of 210? I think that that's closest to 180. So I'll say tangent of 180 plus 30, which reduces to tan 30. And tan 30 is opposite over adjacent, 1 over root 3. What about the sine of 135? Well, this I can reduce to be the sine of, say, 90 degrees plus 45, which is cos 45, which is 1 over root 2. Now, grade 11's matriculants, I want to warn you about something. Do not use 90 degrees or 270 for a tan. Remember when we learned cofunctions, we specifically said they only have to do with cos and sine. So don't use them for a tan. We don't know what the tan of 90 degrees plus theta becomes. We never learned this. So don't use 90 degrees for a tan if you're given a question. For example, if you're given tan 120, please do not say this is tan of 90 degrees plus 30. No. No, no, no. Instead, go for any of the other terminal angles. Maybe go for 180. This is 180 minus what? 60. Which becomes what? Negative tan 60. And what is the tan of 60? Opposite over adjacent. So root 3 over 1. So this is now negative root 3. Okay, so don't use a 90 or a 270 for a tan. Let's do a short classwork. Grade 11's matriculants, why don't you pause the video and try to simplify this on your own and see what you get. So the cos of 300, I'm going to rewrite as the cos of 360 degrees minus 60 degrees. The tan of 150, I'll write as the tangent of 180 degrees minus 30 degrees. Be careful to not use a 90 there. The sine of 225, I'll rewrite as the sine of 180 plus 45. Now remember, cos of negative an angle is just cos of that angle. We learned that in part 3, negative angles. Or part C, negative angles. Now, the cos of 360 minus 60. 360 minus something is where cos is positive. So this is the cos of 60 degrees. And tan of 180 minus is where sine is positive. So this is negative tan of 30 degrees. And in my denominator here, I have sine of 45 degrees times the cos of 45 degrees. Now this means that in my numerator, I now have cos of 60, according to special angles, is 1 over 2. So it's a half, right? I have a half times negative tan 30. And tan 30, according to my special angles, is 1 over root 3. This is my numerator divided by my denominator. What is sine 45? That's 1 over root 2. And what is cos 45? 1 over root 2. So what I actually have here now is negative 1 over 2 root 3 divided by 1 over 2. And this becomes negative 1 over 2 root 3 times 2 over 1. This 2 can cancel that 2. So what I'm therefore left with here is negative 1 over root 3. Great, I hope you got that right. If you struggle with any algebra, multiplying of fractions, especially when it has variables and everything, I suggest that you watch our videos on algebra. Now, I want to teach you guys a trick question that they love to ask. Before we go to that trick question that they love to ask you, grade 11s and matriculants, I'm realizing that this guy here, sine 180 plus 45, should actually be negative sine 45. We know that 180 plus is where tan is positive. And so in our denominator here, we'd have negative 1 over root 2. So we'd actually end up with negative a half. And so our answer here would be positive 1 over root 3. Great. Here's what they like to do. They'll ask you to simplify something like sine 35 over cos 55. And you might be very confused on how to do it, but I want you to note something really important here. What is 35 degrees plus 55 degrees? What's the answer to that? That's 90 degrees, isn't it? So that said, whenever you see a question like this, change only one of them using cofunction identities. Now, what do I mean by that? Perhaps you could change your numerator. Let me just make this a bit smaller so we have space on this side. See here, I could choose to change the sine of 35 to be the sine of 90 degrees minus what? 55 degrees. Remember, we do this because this and that is the same number. 90 minus 55 is equal to 35, so I haven't changed the question. I'm going to actually leave my denominator alone, not disturb it, cos 55. Now, what does this become? Remember, when you have sine 90 minus an angle, that's just the cos of that angle. So what you now have is cos 55 over cos 55, and you can cancel this with that, and the answer is actually 1. Now, here's a similar example. If you add 62 with 28, you should get 90. But this time, I'm again going to change my numerator. You can actually choose to change your denominator so long as you leave the numerator alone, right? Change only one of them. But again, I'm going to change my numerator. I'm going to say this is the cos of 90 degrees minus 62 degrees, all divided by the sine of 62 degrees. Now this, my numerator, becomes the sine of 62 degrees. My denominator, sine 62. So these cancel out and you get 1. Why don't you try this question here? Try this question. I'm actually not going to answer this question. Leave your answer in the comments and see if you get it right. Now, I want us to do a past exam. So grade 11s and matriculants, you now know everything that you need to know about reduction formula, and you can do past paper examples. Except for grade 12s, You guys still need to know compound angles and double angles, and I will cover that in a separate video. But go ahead and try this question. Grade 11s, you know everything that you need to know. There's nothing else that you need to know now. It's all provided in here. So how about you try to simplify this without the use of a calculator and compare with what we will get. I'm going to change sine 120 to be 180 minus 60. I'll change cos 210 to be the cos of 180 plus 30. I'll change tan 315 to be the tan of 360 minus 45. Have a look here. Cos 27 sine 63 is what I was just talking about. 27 plus 63 is 90. So I'll change just one of them. Let me change the cos 270 to be 90 degrees minus 63 degrees. In my denominator, I have sine 63 times. Now, what do we do with this big number? Remember, you can add or subtract 360 at any point. So I'm actually going to change this to become 360 degrees plus 180 degrees. 360 plus 180 gives me 140. Now let's reduce everything. We're now going to have positive sine 60 times negative cos 30 times negative tan 45 times positive sine 63 divided by sine 63 times positive cos 180. Now, the sine 60, according to our special angles, is root 3 over 2. So we have root 3 over 2 multiplied by negative cos of 30. Now, negative cos of 30 is also root 3 over 2. And negative tan 45 is negative 1. And this sine 63 can cancel with that sine 63. So what I have in my numerator is this. And in my denominator, I have cos 180. Now, you're supposed to know how a cos graph, sine graph, and tan graph work. A cos graph looks something like this. It starts at 0 degrees and 1. Then it goes to 90 degrees and 0. Then it goes to 180 degrees and minus 1. Then it goes to 360 degrees and 1. 360 degrees and 1. 0 degrees and 270. 180 degrees and minus 1. So the cos of 180, as you can see, is minus 1. So what is root 3 times root 3? So firstly, the minus and the minus will become positive, right? They're multiplying one another. But what is root 3 times root 3? That's just 3. And what is 2 times 2? That's just 4. Okay. Divided by negative 1, right? Which means what we end up having here is just negative root 3 over 4. Oh, sorry, negative 3 over 4, no root. Okay, so this is how you answer a question like this. Now, much like any other topic in maths, you're going to have to do a lot of practice. What this video has done is given you all the tools that you need to know. Remember that I do link the notes in the description box below. Feel free to click that link and now have access to all the notes that we were working through here. Please leave a like on the video, leave a comment, and share the channel with your friends.